again potential formulation. And what I will try to present over here is it in some sense unifies the formulations of phase field models for pure materials and what you have been essentially seeing in the KKS model. In that, it takes care of the deficiencies of what were happening in the WBM model, as I illustrated in the morning, and it does it in a unified way, in the sense that what you do for the pure materials is also replicated for alloys. Okay? So the same way, so the formulation or the methodology remains exactly the same. Okay, so before I go there, I will present to you essentially, or I'll start from where we left, and which was the KKS. So we'll see that. Let's write down the function now. Okay, this is your functional, and what we decided to do was to have the evolution equation given by this variation derivative, which essentially evaluates to something that you are now quite familiar with, which is and as we saw in the morning, this, if you take the derivative at constant c, this essentially evaluates to minus okay. This is what it evaluates to, and we refer to this term over here as the driving force of the problem, because essentially this can be written down as and pictorially what this is essentially as we saw, I were to compute the driving force for phase transformation at a given position, essentially do this as the parallel tangent construction, and the driving force is essentially the distance between these two lines. Okay, this is what this one is. Alright, this is what we covered in the model. And this naturally brings to the conclusion that as you vary mu, so mu is essentially the slope. As you are going to vary mu, there is a special mu for which you will have a situation where the two parallel tangents coincide, giving you the common. Okay. So this will happen only for at a given temperature, a special mu. Okay, not all mu's will do this, only a special mu. GS and CL curves, it will happen only there. And at that mu, these two will become equal and the gravity constant. Okay. So this is what we saw in the KKS. So what are the details of that formulation? You need CS and CL to be computed, such that they are part of the parallel tangent construction. So you will have them satisfying this property, and that decomposition giving rise to CS and CL, which you can use in the differential. Okay, so now to bring in the unification, we will just revise what we did for pure materials as well. What did we do for pure materials? We wrote down the functional over here, which was just to write unified way is also the unified way to do it. You have this, right? It's just the same way as writing this, except that I'm not using the difference, but I'm writing it as well. This is possible because I can take always the liquid as a reference and write it the way that we have written before, but just to make consonance with what we had, just to make that uniform, right? You can start here, and as you did over here, right now the evolution equation as that, which would give rise to, you all know by now, and this will give you minus. Okay, this is what you will get. Now, this is essentially, now just to make equivalence between these two pictures, right, I will do an excursion, try to tell you to do a construction, alright. Let's say a energy curve of this type, and what I'm going to ask you to do is, let's say I draw a line with a tangent at a given point here, and at this point you have a slope given by mu, right? And it makes an intercept over here, which all of you agreed is, if this is F, C at this point is see that's minus mu C, right? If I were to now represent the same information that I have here, but not with F as C, but with an alternate choice of variables, where the variable is the slope of this line and the intercept it makes. Okay? So I'm representing the same information that you had before, F as a function of C, but now instead of plotting F as a function of C, I want to represent that information by plotting how the intercept changes as we take the slope. Remember, for each composition for this type of a curve, you have a unique slope, right? The slope will not be repeated. That means for a given composition, you have a unique mu, and so as you go and change composition, you have a unique set of slopes that you in the problem, and for each of those slopes, essentially you have the intercept, right? And since these are tangents, what you will get out of the envelope of those tangents will be the curve itself, right? So essentially, you are not losing information, but representing the information separately. So I'm going to call this variable, give it a name size, and what I am going to ask you to do is to plot this variable size. Since I am drawing this tangent at a given composition, I'm going to ask you to draw how as psi vary with mu for this curve. Yeah, that's the point. So I'm therefore asking you to do a transformation like this. For a given mu, you have a unique C. Therefore, for each composition that you choose, you compute the mu and compute this value. So the mu to C mapping is unique. Right? How does this curve do? This is the same question I asked you yesterday, but for F and G. How did F as a function of C look? How does this look? Here you don't have a priori information. What there you had dou F by dou T, what it meant. That was F to T. Here you don't have that information, but you have a pictorialization of what I'm trying to do, and therefore what will you do? It will be a curve like this. Okay. Everybody agree? It will be a curve of a decreasing curve, right? It will be a decreasing curve of this type, and it will not have constant slope because here it is doing some sort of activity and then it is getting converted. Okay. So essentially, have a curve like this. To predict the slope, you can do a calculation as you did for the previous part, dou F by dou T, right? If you take dou psi by dou mu, and if phi is defined by this, what will dou psi by dou T be? This is the outer side, and I'm telling you to compute dou psi by dou T. Okay, I will initiate. Remember, C is implicitly dependent on mu. Okay. Is that okay? F has an explicit dependence on C. C is mu. So dou F by dou C times dC by mu minus mu dC by mu minus C. Now what is this? So this and this will cancel. You're left with minus C. And what is happening as you go from here to here? Is C increasing? Increasing, right? And C is the slope of this line. So it should get more and more. Correct? So instead of entropy, you have composition. So you'll have a curve like this. Is everything clear at this point? Yes.
One question. So if you have a miscibility gap,
We'll come. Let's have a function of this type. Right? C has to be a unique function of mu. So that is why I have created a curve. Alright? Everybody in sync? Now, let's say I draw another curve. So let's say this was solid and this was liquid. Right? It will have the same curve, right? It will have the same behavior like this. It's also shaped similarly. But in contrast to what these curves do, this essentially has a unique intersection point. Right? A unique intersection point where what is happening is the value of psi is equal. That means the value of psi of the two curves are equal at the unique value of mu. Okay? What does this intersection point represent? No, I mean, what does this intersection point? This is obviously the effective chemical potential. What does this intersection and equality of psi thermodynamically represent? That's essentially the common term. Right? Why? Because the signs are equal and it is at that nice mu when the intersection happens. The signs are equal and therefore that is the common term. Right? So what did you do over here? You transform the information of F versus C, which was there like this, into an information which is here. And if you now make a analogous comparison to what you did with F versus T the other day, you had TM over here, which was the point of equilibrium where F has empirical became equal. Here, at a unique effective chemical potential, your psi are different. And that's the point of equilibrium, right? The same as this is the point of equilibrium. Okay? So it's an analogous transformation where F changed to psi, T changed to mu. Okay? Which happened, as I said, in the KKS model accidentally. But here, there is a formal mechanism by which it is happening, by this transformation, where I am writing this whole thermodynamic information in a slightly different way by constructing this side. Now, because of this, I am going to be inclined to write, as I did here. What did I do? I wrote down the total free energy of the system as the interpolation of the two, where Fs is a function of temperature, Fl is a function of temperature. And since these two pictures look exactly similar, I am inclined to do the same here. And write down this. Where inherently, because my variable is the effective potential, naturally becomes this. Right? The consequence of this is what? We just derive minus C. But then, this is the solid transformation. This is the liquid transformation. If you do it this way, what we essentially will have is that C is equal to Cs agree? Okay. So it is basically following from what we started yesterday, of what we formulate as the free energy formulation, right? Or you constructed a potential of this type, which upon differentiation with the respect to dependent variable gives you something like this, which is the constraint that we use in the KKS model as an arbitrary condition. Now this follows from the thermodynamics. Correct. Alright, it's not arbitrary. It has to be. Alright. The fallout of of this is, therefore, that all I need to do is to change what I formulate as my functional. Instead of calling it a functional, which is looking like this, I will change and construct a formulation or formulate a functional which is directly based on this, right? And I'm essentially going to be done, right? Because as you will see, I will recover back the same estimation that we did for the case of the KPS model, except that everything just falls into this automatically. So we'll create a functional, and since it is a functional that is coming out of a transformation, we're going to call this all the other parts remain the same. But here I use okay, this is what I want to do. And my evolution equation for phi is going to be dot f of this. So if you do a variation derivative of this, what do you get? So who will tell me what the variation derivative of this will be? Remember, this derivative when I am taking, it is at a constant mu because I want to have a separate equation for it. Okay? So mu and phi are now my independent variables. So when I take this partial derivative, it is at a constant, right? So psi s of mu minus psi l of mu, h prime of mu. Phi, this is your evolution equation for phi. Agree? So what is the expansion of this? Minus fl minus mu cl times h of prime of mu. This is what your KKS model was, right? But it came down in one step. So they started from a different function. Okay? Magic, right? Just for a change of variation. Right? I mean, it's not, if you look from a thermodynamic point of view, all we did was go to asking the question, what is the thermodynamic driving force of the system, and construct a potential based on the thermodynamic driving force of the system. Okay? And thereby it comes out the same way the pure materials things comes out. So there also the starting point was asking what is the thermodynamic driving force of the system. Right? Not the effective energy of the system. Thermodynamic driving force. As you ask that question, this is the natural outcome. Okay? Now the only question that remains is, you can't solve this equation. Why? So this is the mu sitting there. You need evolution equation for mu. Alright? But that is, as you all know, going to come from a heat conservation equation, just as you required an energy conservation equation for the temperature T. You started from dou E by dou T is equal to del dot K grad T. Create the evolution equation for the temperature T. So you start from a conservation law. Here also you will start from a conservation law, which is the mass conservation law, which is going to be the following. relation that you get from, because psi is interpolating like this, the computation directly follows. Right? This interpolation directly follows if you write psi as this. Right? And therefore, I just have to make a transformation over here. Remember, CS is a function of mu, CL is a function of mu. Alright? And there are two terms which are dependent on the time here. One is mu, and one is v. You independently take by chain rule the time derivatives. Okay? This is your evolution equation. You will introduce what is this? You need derivative. That's your evolution equation. So all you need to know is to now introduce variable over here. This is typically referred to as a susceptibility. Okay? Because it's derivative of the field with respect to the mu. So we can write this as alright. This is what you will get. That's essentially susceptibility. I'm going to introduce this term. All of you have heard about magnetic susceptibility, right? It's a similar term. It's relating the composition which is derivative. Energetic. So you have an equation like this. And to make sense of it, you just have to do an analogous comparison right. The H prime by the dt sorry. Have to be careful here. Okay, this is the equation that we derived out of the temperature field and the energy evolution equation. This is what we have derived out of the composition equation after starting from here, which is the mass conservation equation. And look at the nice feature of these equations. See, physics is all about symmetry. You must have symmetry in different fields of similar types. The evolution equations of those fields also will be sharing some features. Okay. This is both are intensive variables. These are diffusive terms, right? This is the flux. This controls the flux of the composition. This controls the flux of the enthalpy. This, as we go here, what is this? Which is the source term that quantification happens. What is this term? Just to make your life simple. What is that term? when solidification happens in an alloy, right? Here, when solidification happens, what happens in front of the solidification interface? So here, what is rejected? So here, solute is rejected. So this is repartitioning of solute. Here, repartitioning of interface. Okay, this latent heat is repartitioning. Exact similarity in the equation. Right? Same principle is what we use for the pure material and in this case, no deviation. Not only that, your equations are exactly the same, derive much more simpler. Okay, remember the KKS model? You have to bring in 2 or 3 theorems together to get the derivation done. Then one-step derivation, just as it for the pure materials. Right? And that's the beauty of it. It unifies everything. Right? It unifies everything in the sense that once you have identified the thermodynamic driving force with the right variable, you can essentially formulate any history. Right? Right? And because of the structure, I don't need to rederive anything because at equilibrium, all of you have agreed at that mu, this 2 guys will become equal because they will intersect. So the resultant equation will be contribution of only these 2 terms. And dT phi equal to 0. So the structure of the equation on the phase field interface will be directly a function of A and W as it was in the original chemical model, as it was in the case of the pure materials, as it was in the case of the KKS. Right? So you have complete independence of what the alloy thermodynamics, which is here, and the interfacial properties that you want to add. Right? It's just the mechanism by which you go. Any questions?
Essentially, what seems to be the difference is that in case it's minus mu CS minus CL, and here it's mu S CS minus mu L CL.
No, it's exactly the same.
No. Here it will like psi. So, but the system is not when the system is not in equilibrium.
Yeah.
So it will be S minus mu S CS. Right. So mu S and mu L are different.
Mu S and mu are not different, precisely because they are always on the same mu. The difference is such that they are at the same mu, just as it is in the pure materials, which is at the same T.
What is the difference?
There is no difference. Except that I am just changing the variable. There is no CS and CL anymore in some sense. It is just mu sitting there. Okay. So the difference over here is only that I constructed a functional which is having its independent variable as mu itself. And therefore, when I take the partial derivative with respect to phi at mu constant, this is the partial derivative. Right? I don't have to take an arbitrary differentiation of dCs by dP and dCl by dP and bring that all together to get the same thing. Okay? It is automatically happening. Okay. Right? And thereby, it makes my life very elegant and simple. And we are done. Right? We are essentially done because we now have a solidification problem of alloy thermodynamics, which can be extended to arbitrary number of modes. Yes?
So the C updation, that is a new updation.
Yeah, but C is updated from you. This fundamental relation does not change. So if I have mu, I will have C.
So you did an inverse function already.
No, I mean, it's just a interpolation function because I have CS of mu and CL of mu, which, as I said, because of the unique mapping that I have between C and mu, this is an invertible function, which means I can always do that. Alright? Fun, right? Huh? Let's take an example. Where do we take an example?
Also, with the x-axis, you are writing C out.
Where?
The plot.
Yes.
So, you have to watch out if it is in multi-component, what we should do when we want to convert to fractions.
We can do it. We just have to choose the right reference space in some sense. It is not very difficult, particularly because the solvent and the solute and the solvent description that we started with are exactly the same that I will do. That doesn't change. You only have to attribute what is the solute, what is the solvent, what is the solute. And once you have done that, the effective chemical potential is something that I can also do. So, for the case where C is equal to the mole fraction by the molar volume, this fundamental relation will hold always. And all our models, even the KKS model and even this, the inherent assumption is the molar volumes of the components are actually equal. That's okay.
Locally, we have to.
It is all equal in the KKS model also and here as well. If you do not make that assumption, you will naturally have in the liquid flow when systems move, or there will be stress in your material when diffusion happens. But since you don't consider either of them in your actual thing, the actual assumption is that the molar volumes of the species are all same. And if the molar volumes of the species are all the same, this is just a scalar convert molar function. This is not right. You know, set some sense. All you did was a reformulation of the problem. Okay. Now,
is the grand potential unique, or we could have got it away with any one-to-one or two formula, like decreasing function from mu to anything?
okay, just to give you a more thermodynamic perspective of this. The grand potential has a unique space in thermodynamics. Pressure, grand potential density rather. Grand potential density is directly pressure. Okay? So difference in solid and the liquid grand potential densities is directly pressure difference. And pressure difference
Partial pressure.
pressure difference between the solid and the liquid. Okay? Unless you are thinking of a driving force pushing the system, right? Effectively it's a pressure. Right? This is directly pressure difference. Directly, therefore, this is the natural choice thermodynamics. In the case for the pure materials, the grand potential and the free energy are interchangeable because for a unique component. G by N is directly mu. Okay? Because of that, for the pure material case, Fs minus Fl is directly pressure difference there as well. Okay? And thereby, a driving force having a direct connotation with pressure makes absolute perfect sense thermodynamically, and therefore it's not a surprise that you will do this. Okay? So the beauty of physics is all things fall in place at the same time if everything is right. Right? That's essentially what I mean. Right? Now, what is that? You have the evolution equation for mu and your phi evolution equation. What is that? 2 over 2, 2. Huh? Well, the idea is how you convert it into multi-component space. So this is something we will do very quickly as a very quick. So, for the case of multi-components, this particular equation, remember this is a effective potential, which means it is mu A minus mu B. That B is essentially a solvent. Okay? So, in a multi-component space, let's say I have a nickel-based superalloy. Nickel is in vast majority, all other components are in small majority. So, typically, the solvent is the nickel. Okay? So, you will typically write down this as this is the transformation that you use. This is the partial derivative you all have been used to. When all other components except the solvent and I are changing. This is of course with the solvent and all other components are fixed. Alright? Take a derivative with respect to that. I mean, the difference is what we want. So as I said, you can picturize this as the same way that you did for the how the diffusion is going to happen. Why I am using this? The idea is that the substitution is happening between atom here and atom there, and thereby the energetic difference is when I'm changing the relative change is happening. So this is the motivation for using UI. So all that.
Should we not consider the locally present phases FL, FL?
It will automatically happen because the chemical potential flux will be dependent on all sorts of possibilities. Okay, so the flux of I will naturally depend on M okay, something like this, where J is varying from the we are into programming, so we will start from the n component system 0 to 0 to n minus 1. Okay, because last component is this one.
But the compensation is conserved no side
Component is not
No, no. Don't solve for all the compensations, right?
yeah, that's why the last component is
So minus 2.
0 to n minus 1. The last is include n minus 1. Good. N minus 2. That's your composition space. Right? That's your mass flux. What is Mij? Mij is the mobility. Okay? And this has direct relation with the diffusivity. D. Okay, these are different, written in very different ways. Essentially, what you have is this. You can also write it as this with the mobility times the dVdc comes over here, but both are interchangeable because this is just the inversions. Right? This is the Hessian matrix, and this is the reason in the MicroSim software you actually need the Hessian. This is the thing that controls the mobility, as well as one more interesting property that you will see. So this diffusivity is something that, so this is written in the matrix notation. So yeah, so it is correct. It is correct. And once you have fixed the mobility, you essentially can just write something else. Okay. So that's your diffusion equation, which you can recast it into the mu equation readily because Ci is directly a function of mu. We write it for two phases. We were writing Cs below or above? Huh?
GPSC wants S to be on the superscript. Phase should be on the superscript.
Yeah, but what are we writing?
We wrote always down.
Down. Right? The point is here it is coming down. So by notification it should come down.
Side. Top is better because bottom is meant for the species, top is meant for the phase.
So we will turn off this. I looks better downstairs. Okay, for 2 phases. For n phases, all we will do is interpolate with a multi-phase equation. That's all that will change. But when you put this equation over here, okay, I want you guys to tell me so if I put it over here, and remember I'm writing in system, and the implied thing is that these are all functions of mu. And now remember, it's not a single valued mu, it's mu of all the components. Okay, so static, when you write down, this is a bold character. Here I can't use a bold character. So what I will do is I will mark a small thing over here telling that it is not one chemical potential, but effective. This is the chemical potential of all the species. Therefore, when I take this derivative, how will it look now? When I take this derivative, how will it look? You have each term dou c by dou mu I times dou mu I by dou v has to be a sum, right? So you will essentially have I'm going to write it like this. This is a matrix by definition, right? Times d mu I by dt, right? And this is essentially the interpolated sum. So I'm going to take dc by d mu times h of t plus dc by d mu 1 minus h of t. So I'm going to write it as a total thing, which is a function of t by definition, right? So this is a matrix multiplied by a vector, which is d mu I by dt, right? This is equal to del dot this plus is that correct? Make sense? You had CL minus CL before, but here when you take a time derivative with respect to P, only that particular component will come, CL minus CL, and that's what we will do, right? Huh? Oh, good. So how do you solve for mu? How do you solve for mu? Huh? Here is where the most expensive part of the computation is going to come. Okay, So this is a vector containing all the components, right? Each line is a for the ith component we have n minus 2 here. This is a matrix which is n minus 2 cross n minus 2. Matrix inverse times this gives you the dvy by dt, all of the same time. Okay, so every step of the computation, what you need is a horrible looking matrix. Yes, sir.
That is the initial.
Horrible matrix inversion. So for two components or for ternary components, you can hard code what the matrix inversion is going to be. But as the number of components are going to go up, we'll have to do the matrix inversion all the time. So basically, from the KKS, which had an iterative solver, having multiple matrix inversions at the side, we have reduced it down to one single matrix inversion. That's how that's okay in terms of the computation effectiveness. Right? So this is how your multi-component diffusion equation will look. The phase field diffusion equation will essentially look very similar to what the matrix looks. So this form remains exactly the same, except that now this is a function of all the chemical potentials, all the diffusion potentials or effective chemical potentials that are going to be. And how does that look? How does it look? It looks precisely so. This is how your transformation is. Once you have defined it, it becomes a function of all the views in this manner. And once you have then transformed that, then writing this minus this stack and procedure, which is exactly the same as the binary. Okay, so the extension from the binary to multi-component was essentially quite trivial, right? The only thing is, in the pure binary case, this inverse would just mean 1 by dc by dt, which is d. As soon as you have multiple components, it requires an inverse. That's the not nice part, but something that you pay for having a nice elegant form. Right? Good. Any questions? So we have reached and unified everything that we have learned, right? We have understood why WBM is not correct, right? Well, not correct in the sense that there are limitations to its usage, but the KKS and the GP are effectively doing the same thing, except in the GP you are essentially formulating something which comes out naturally, starting from the bottom. All right? You do not have to per se introduce the concept of phase compositions, right? If you ask a physics student what is a phase composition, they will start scratching their head and listen, what is a phase composition? There's a composition, there is a phase fraction. What is a phase composition? So that construction is a slight engineering line to it. But if you look at this is a field. And if you define it as a field and the phase composition as something that functionally follows from a field, that's fine. Okay. So although both are correct, because the composition makes it feeling. Effectively both performance and theoretically. Performance-wise there's a difference because in the classical KKS model, you actually store all the phase compositions, right? So if you have two phases, you have two phase compositions, and there's so twice the overhead. Whereas here you just store the calculation. You don't need to store this. You can directly compute it off. Okay. So there is a 1/2 overhead that you reduce. Apart from the iterative procedure that you typically have for getting the CS and CL again. You don't have the iterative procedure. Okay. Because the same is directly a function. Right? So you have gotten rid of a very costly iterative procedure. That cost of the iteration actually goes up as the number of components go. You gain in memory and gain in effectiveness.
Did you compare the computational efficiency?
Yes, of course, the case is clear. There's no doubt. For each of those compositions of the things, you typically need 3 to 4 iterations. I mean, at the start you need more, but then you reduce down as time progresses. But typically you need 3 to 4. Whereas in the Gantt potential, that same composition will be done out of one single operator. This inverse is being done internally during the iterative process because this is part of the Jacobian. So when you do the iterative process, this is being done number of iterations that you do. Okay, which you do only once. So by nature of the construction, you essentially are quicker than the GKs by design.
It's very simple to understand why dmu by dc will be invertible in a multi-component space.
dmu by dc, as I said, if it's a single valued function,
That is understandable.
always concave, you will always have it. But that is not a limitation. I am always at liberty to, even if I have a visibility gap, to locally convexify my function. Not deliberately, but by choice. Because remember, I'm not going to functionally do this, but when I'm solving for CS of mu and CL of mu, remember I cannot invert it anymore, but given a C and P, given the choice of C that I'm starting from, that I just start with a guess, I can still invert it to the nearby. That is relevant. Okay, so it is not a direct function anymore, but something I can derive out of the classical KKS relation that is anyway there. But this relation is something that is there in KKS. To find the mu at a given C and P, I will just have to give the guess nearby the original equilibrium compositions, and you will land up at the x. So even if there is a miscibility gap, I can get the effective mu and thereby complete my composition. That's not a problem. That's the same thing that you do in a KKS bias. You basically give the CS and CL nearby the effective equilibrium compositions in the common tangent, such that you're always nearby the right solution. Okay? So effectively you come back to the same thing. Yeah, absolutely. You put the two constraints together, C and P, and with this, the inversion of this iteratively, because there is no thing, you will get back the same thing. So this is what we do when we are actually taking in real thermodynamic databases. Because the real functional forms will have functional types of this type, but then you have a numeric composition as a function of P, not a direct functional form. Okay, any other questions?
Actually, I was not getting.
Yes, which one did you not get?
CI by 20 and CI equations, how are they? The extent of those two equations.
You mean here?
Yes, sir. Those two equations, and after that, what?
From here to here?
Yeah.
So when I write down Ci as a function of Ci, which is a function of mu1, mu2, mu3, mu4, mu5, okay? So when I take a time, all of them are time dependent. No? So I will take a chain rule. So I by mu y times mu1, mu2. So if you think about it, this, if I write it as a vector for all the k components, it will be a matrix multiplication of dc by dmu times du by dt. That's what I will do. Plus, there is another derivative with respect to phi. So it will be just ci minus c, cs minus cl of that component, which will turn up here. Okay? So what you have here is, you will essentially have a matrix. What all the k components. Similarly, you will have this as a vector as well for the k components. So to solve for all the updates of you have to invert it.
Putting the three terms, we can understand it if we start between the remaining points. It sort of wants to split, right? There is the composition of the split because it remains the field. In grand position terms, because it's a common tangent.
Yeah, but I mean, essentially, you remember that construction. I am just interested in the driving.
But I am at a point which is initially in the middle, and that belongs to the common tangent. So it's already there in the common tangent.
If it's already there in the common tangent, the corresponding mu is the same. The yes and mu.
So it's not going to split.
No. No, the mu is the same.
No. So if the system is C,
if you are here, and C and P correspond to a percent here, your mu is all constant along this line. This line is what this is. The mu is not changing. So whatever composition you pick, that is just defining you how the composition will vary across the interface from CS to CL. This is the variation. The composition will vary. It's not a sharp interface. The CS will be a function of P, but that is the function. That's the common tangent line.
adapt the system towards a non-equilibrium state, I will change.
For non-equilibrium, your composition of the liquid, so you have your P energy of the liquid has to be here. Then you introduce so your chemical potential cannot be on this line. If your chemical potential is not on this line, whatever you do, it's an equilibrium. If your chemical potential is corresponding to the composition here in the liquid, that is what you initialize the system with, you naturally have a driving force. Okay. Good. We have made excellent progress. Unification of close to 94 onwards to 2012. How many years of work? How many years? 10 plus 12. 10 plus 12, right? 1994 to 22, 22, 12. 18 years of country. No, 94 was the WBM. It was the incorrect one. But then there were solutions.
The WBM model is just interpolating the slope.
Yes.
Like
yes.
Here they interpolating the sun.
Yes.
It's a huge thing.
Yes.
But for the diffusion argument that you made for non-substitutional diffusion, it's essentially the same. That was an argument.
No, what I'm still using the slope for the diffusion.
No. The argument was that for substitutional diffusion,
yes,
it's always the slope.
No. I'm not talking about that. The mu that I'm using the diffusion equation is the slope.
Okay.
I am constructing using that mu a potential. That is all I'm doing. I'm still solving for the diffusion equation. I'm not transferring it into a separate equation where you are doing dou Tc is equal to del dot m dou psi by dou mu. I'm not doing that. That is a separate equation. That's not the correct equation to solve for mass diffusion. Mass diffusion equation still remains this. Okay? So that doesn't change.
You mean not having the variation?
Yes. As you do in the classical free energy formula. This would be dou f by dou c, no? I'm not doing that.
No, it will become ln.
No, forget about ln. Because it's a separate equation. cosine by tau mu. Okay, this is the classic. This is what I am doing even in the temperature evolution equation. I am not changing Fourier's law. Del dot k grad t. I am not going to change this. This is the fundamental law. Mass diffusion is still going to happen this way, except that the potential is changed. By the way, what is this construction that I did here? Can anybody tell me what this is? I transformed f versus c to an intercept versus the slope. So the classical Legendre. You basically did a Legendre transform from your free energy to potential which is. Mathematics, people keep doing this, change of variables quite a lot, right? And makes things simpler as you see. And you have just changed the natural variable to its conjugate variable. Excellent. So we are good to go for dinner.
This time.
Yes.
See, even in superconductivity, right? The rest of temperature and yes, temperature is fueled by interaction. Chemical potential is fueled by density. And whenever you want, you invert